Good morning, everyone. Thank you for coming. I'd like to thank organizers for giving me an opportunity to talk about my recent work. So I'm going to talk about the dynamics or dynamical response of a weak model insulator. We have developed a sort of a new numerical approach that can calculate the dynamics for a wide range of U over T and temperature of the Hidemaro without a restriction of dimension, lattices, and electron fitting. So I think this is a very powerful method. And we can easily calculate this kind of spectrum. This is an example of SQ omega in the ground state of the Hydra coplanar magnetic order on Collaborators. So I'm going to try to explain what we are doing for calculating this kind of spectrum. So the collaborators of this work are Chen from Kenya, Kipton Bowers from Leno, Los Alamos, and Christian Batista from University of Tennessee and Owner, Oak Ridge. Okay, let me start with a brief introduction to 5D electron systems. As it's known well, the transition metal oxide shows interesting phenomena like metal insulator transition and high DC superconductivity. And we can understand metal insulator transition in the following simple picture. That is, if the Coulomb interaction is larger than the bandwidth, it's going to be insulator. And Cuprate has this kind of two-dimensional structure forming a square lattice. So how about 4D and 5D electron systems? So 4D and 5D orbiters have spatially extended orbiters than 3D electron orbiters. So it's not sure that it's going to be metal. Indeed, 4D electron system is a Fermi liquid. But perhaps surprisingly, the strontium iridate is an insulator because of strong spin-orbital coupling. The iridates form the kind of the square lattice similar to Cuprate. So it's interesting to compare what is the similarity or difference between 3D and 5D electron systems. So perhaps I don't need to go detailed about the origin of the J-effective 1/2 orbiters because many speakers already talk about it. But let me try to remind you of the main point. So if the Coulomb interaction is large, the T2G band will be split like this. It's going to be a simple model insulator, but it's not the case here. And instead, the system has strong spin-orbital coupling. Then T2G orbiters are split into J-effect 1/2 and 3/2. And so even though the Coulomb interaction is small, the bandwidth is also small, so it's going to be actually insulator. And this is a simple diagram of the level structures. In 5D, T2G orbiters is split into these guys. And the wave function of the J-effective 1/2 is something like the linear combination of these wave functions. Okay, so let's look at spectrum. So this is a RIX data of strontium iridate. And we can identify the magneton dispersion in low energy region and also the electron hole continuum in kind of higher energy scale, but still the energy scale of magneton is just half of the electron hole or charge gap, which is relatively small. I'm going to come back to this fact later. So if you connect the peak position of the magneton spectrum, we can find a kind of sharp magneton dispersion, which is somehow comparable to Cuprates. This is a magneton dispersion with Cuprates. So there's some difference, something like it's not easy to compare because wave vectors are different. This is almost flat here, but there is some difference at I 0 and pi over 2, pi over 2. And another interesting point of the strontium iridase is that some people found the Fermi arc upon electron doping. So in this paper, they conducted the electron doping several fluctuation using a surface coverage, and they found this interesting Fermi arc, which can be comparable to Cuprate or 3D electron system. So it's naturally it's interesting to compare what is the difference between 3D and 5D electron orbiters. So that is one of our motivations. Another interesting point of this strontium iridate is that some system shows a gigantic magnetic response. We created this kind of superlattice forming STO and SIO layers, and we introduced the several STO layers, try to separate the SIO layers in realizing a quasi two-dimensional systems. And if you measure the order parameter using the X-ray scattering, and we found the net order or crossover temperature increases rapidly as a function of a magnetic field. We applied in-plane magnetic field only, for example here, only 0.1% of J. Only 0.1% of J magnetic field increases 50% of crossover temperature, which is amazing. And we found that this material has several interesting features: large dim interaction, hidden residual symmetry, and 2D critical fluctuations. And these interesting features can account for this interesting phenomena. So actually, this is interesting, so let me try to explain the hidden residue symmetry. The major interactions of Hamiltonian is written by the Heisenberg term and dim interactions and anisotropy term. We applied magnetic field. And this material has an interesting feature that is, if you sum up the dm vector or Moria vector in a loop, it's gonna cancel. So this is kind of unfrustrated condition of Moria vector. So if this is the case, there is an interesting unitary transformation. So we can rotate the spin difference frame. Phi is defined by this ratio of energy scales. And we rotate phi for sublattice A, and we rotate minus phi for sublattice B. And we can map exactly this original Hamiltonian into the SU2, apparently SU2 symmetric interaction. That is a Heisenberg term, and rotated the magnetic field. And another point is that we can couple the magnetic field and the order parameter linearly. So that's why we can control the anti-ferromagnetic order using uniform magnetic field. So motivated by the iridase or the 4D and 5D electron systems, our motivation to study the dynamics of these materials. And these materials are naturally located in kind of intermediate U region in the language of Hidemaro. So this is the transition temperature, net transition temperature and charge gap for this cubic lattice at half filling of Hidemaro. In the case where the U over T is very small, we can use the perturbation expansion like Hartree-Fock. In the case where U over T is very large, we can use spin wave theory. And also at high temperature, we could use the high temperature expansion or simply classical spin analysis. So our target is this area, an intermediate U and finite temperature. So for example, DMFT almost always overestimates the net temperature because the methods doesn't include spatial fluctuation. So that is our motivation. So we try to include spatial fluctuations to explain this finite temperature region. Okay. So we are trying to calculate this dynamical quantity, SQ omega, defined by this equation. So basically, it's the time correlation between spins. So in the large U limit, we have a nice approach using Landau-Richt's equation. In the large U limit, the dynamics of spin is written by the simple Landau-Richt's equation. And in this paper, they studied the dynamics of the spins using classical spins. And they accounted for some feature of SQ omega of this material. So this is a nice approach. So our aim is to extend this nice semi-classical approach away from large U limit and try to use this approach to a wide range of U over T. So this is our approach. So let me explain our static approximation. So this is the original Hubble model. And the interaction term is here. And we can rewrite this term into these forms. And n square and this sz square up here. And here, omega is unit vector on sphere. We can do it because system has SU2 symmetry, rotational symmetry. Then we adopt the Hubbard-Strauss transformation to introduce auxiliary fields for each square. So we introduce the auxiliary field for charge sector and spin sectors. And we take the saddle point value for charge auxiliary field. But still we have the spatial fluctuation for spin degrees of freedom. And finally, we can map to this kind of Hamiltonian. It's similar to Kondo model, where we have the conducting electrons coupled to the local classical spin degrees of freedom, which is m here. Excuse me? Omega? Omega is the unit vector point. Yeah. Oh yeah. So we introduce some classical variable through this one, right? And we combine the amplitude and omega. It's going to be m. So yeah. So also thank you for asking. So length of m fluctuates. So we need to optimize also length of m in this picture. So in this paper, they studied the phase diagram of this three-dimensional case using this effective Hamiltonian. And they found that this model can explain this non-monotonic behavior of near temperature. Because this Hamiltonian captures the spatial fluctuation of the spins, and actually the critical exponents at the phase transition is also correct, O3 universally class. Okay, so this is the formalism for static approximation. So in our calculation, there are two parts. The first one is thermalization, and the second part is the dynamical simulation. So I'm going to explain first thermalization part. So we could use simple Monte Carlo update. So we have the M configurations. We try to update M spin and calculate the weights. And we could use diagonalization simply, which costs the order n cube, which is kind of costly. And we can reduce this cost down to order n using several techniques. And we adapt the Langevin dynamics instead of Monte Carlo. And dynamics is written by this form. And the first one is simple precision movement, and the second is a damping, and the third one is a thermal noise. This is a Gaussian noise. Omega is the free energy of the free electrons. So the point is how to calculate this derivative efficiently. So we adapt the several techniques, the Kerner polynomial method, the stochastic trace estimation, and automatic differentiation. So I'm trying to explain as much as possible these techniques here. So I think you are worrying about kind of the energy conservation or something, but there's no conservation. So this is just noise. So there's no difficult point actually. I mean, you don't need to care the conservation or something much. So at each time step, we calculate these forces and update the spins, and also we recalculate it first again at each time step. Okay. Yeah, exactly. Okay, the first part. Steady state. Yeah, if the temperature is low enough, it's going to be, the fixed configuration, net order or something. So first, I'm going to explain the Kerner polynomial method. But before that, let me try to summarize this formalism. So given the M configuration, the Hamiltonian is already written by bilinear form in terms of fermionic operators. So what we need to do is calculate the derivative of free energy with respect to the local classical degrees of freedom. And free energy is written by these forms, and g of x is this simple function. And here, rho is the density of states. So we're going to try to approximate the density of states in some ways. So as I mentioned, if you use a naive Monte Carlo with diagonalization, it costs n cubed, and which is impractical for the dynamical simulation because we need to diagonalize each time step. So we're going to use these techniques to reduce the computational cost down to order n. So the point of the Kerner polynomial method is to try to approximate density of a state into a Chebyshev polynomials. Here, T is Chebyshev polynomials, and mu is the coefficient. So we use a second kind of Chebyshev polynomials defined by this. And what we need to know is surely coefficient, mu. And mu can be calculated as trace of this polynomial. And this is an example of this expansion. In this case, we have only two delta functions. So density of states is simply the sum of two delta functions. And this cumulative distribution is going to be a step function. And as a function of expansion order, capital M, we can see smooth convergence to the true value, which is good. Then we notice that if you calculate this trace exactly, the computational cost is n squared m. Because here H is sparse matrix actually, because it's kind of tight-binding Hamiltonian. But power of m becomes quickly dense. And to next order, we just need to apply Hamiltonian to some power of H. So it's basically the sparse dense matrix products, which goes n squared. and we need to repeat this multiplication to m times. So that's why m square m, n square m. And here we try to use kind of stochastic approach to estimate trace. So this is what we want, trace of something, some matrix. So we introduce some random matrix, kind of random matrix, R and R dagger. This is just the conjugate. And if R dagger is identity, this is exact. But somewhat we try to use this smaller matrix of R than B, try to reduce the cost. And if you think of the error of this approximation is written by here, and diagonal elements of R dagger is 1, so the error comes from the off-diagonal elements of R dagger. A simple choice of R is simply to fill up with the random variables in each element. So if you think of the completely random matrix with random element, R dagger has a diagonal 1 in some random values of diagonal paths. So actually this doesn't work much. We try to improve this approach using some technique called coloring. So instead of simply filling up with random variables, we try to use some structure of the lattice. So I'm going to explain this technique a little bit more. And idea is, sorry, let me go back. So idea is that the error comes from the off-diagonal elements. And B matrix has some structure. And idea is if the element of Bij is large, we try to set 0. We try to set R dagger is 0. Then the product is, of course, 0. So that's the basic idea. And B is actually like energy matrix or density matrix. And we can see some decay property of these matrices. So this the Hamiltonian has a 2n by 2n matrix. If you think of single band Hidemaro, 2n by 2n. So we can identify the distance between two indices of a matrix. So the element decays quickly as a function of a distance. This is a nice property. So we try to set 0 for large element of Bij, which is large element of these energy matrices. And to do that, we use coloring. So this is an example of triangle lattice. We assigned several colors to each side. So I use 4 colors in this case. And the condition is that we try to maximize the distance between sites with the same color. So this is the kind of optimal solution with 4 colors. So with this choice, the R dagger becomes something like this structure. So most elements are 0, and sometimes becomes the random variables, but with the small element of Bij or energy matrices. And the performance is something like this. This is a test for 1-dimensional and 2-dimensional tie-binding motors. And I introduced uncorrelated random matrix R. The error decays S minus 1/2 in any dimension if you use a completely random matrices. By choosing this nice coloring technique, we can see much better decay, convergence. Sorry, S is a number of column. Yeah, the point is we try to set S smaller than N. That's why we can reduce the cost. And total cost is going to be NMS. Typically, we use N is like 10 to the fourth, M is 10 to the third, S is 10 to the second. So in total cost is much smaller than N cubed, like 1,000 times faster than diagonalization. And we don't need to increase M and S as a function of N. We can simply use some M and S for many system sizes. So it's truly order N. So this is nice performance, and finally, this is what we want the first, which is the derivative of free energy as a function of M, and which is the product of the density matrix, elementary density matrix and this derivative. So this is easily calculated. This is Hamiltonian, and so this is basically element of Hamiltonian. And what we are doing is to calculate this element of density matrix. We use the automatic differentiation. That is, we rewrite this element as a derivative of free energy with respect to the element of the Hamiltonian. And we approximate this trace of energy matrices using a random matrices. And because we have a specific value of R, we already know this form exactly. So if you choose some R, you already know this form. That's the technique of automatic differentiation. Yeah, so point is, so we formally know this equation. And we calculated the ground state for the triangular lattice at half fitting. So we found phases like 120 order, zigzag insulators, spider matter, and paramagnetic matter. So in the zigzag insulator, we found this kind of spin order. And this result is somewhat consistent with the variation of Monte Carlo. So this is the equilibrium case. And the question is how to calculate dynamics. Because we have classical degrees of freedom, so there is no intrinsic dynamics for classical degrees of freedom. So how to introduce dynamics for that? To do that, we import self-consistent condition. So this is, again, kind of apparently similar Hamiltonian, but with some difference. So previously, this M is auxiliary field, which whose length fluctuates in the simulation. So it can be larger than 1 or something. But in this case, we use a self-consistent condition. This one. So it's slightly different. In dynamics is given by the von Neumann equation for density matrix. So this is similar to the Vogel of the density equation. So we evolved the time, we evolved the density matrix as a function of time, also updating a mean field at the same time. And we try to approximate the dynamical quantity into the product of this one. So here the H is original Hubbard model, so this is the exact definition. And we try to approximate this one. So we calculate the dynamics using this equation, and we measure spin at each time and approximate this one as this product. So the reason why we use self-consistent condition is that the dynamics of the spin is conserved. If you think of the dsdt, which is given by the commutation relation with H. So H is the original Hubbard model. The original Hubbard model has this interaction term and commutation, and S and NN commute. And also in this case, thanks to using this self-consistent condition, these guys commute again. So dynamics is the same with the original Hava model. So this is an advantage. So our approach, two parts. The first one is the thermalization part. And we thermalize system and they calculate the density of a state. And given the density of a state, we calculate dynamical simulation using fundamental equation. And we repeat this process many times and take the sample average with respect to Boltzmann distribution. So this is the main part of our approach. And a nice property of our approach is that in the large U limit, this approach is reduced to the Landau-Lifshitz equation. So as I told you that our motivation is to extend the semi-classical approach to intermediate U region, but actually it's in the case. So we did some perturbation calculation for this effective Hamiltonian, and we deduce the effective Hamiltonian in the large U limit, which is actually the Heisenberg term. Interestingly, it's the same with the quantum case. And also for the dynamics, this is a spin conservation equation, and J is a spin current operator. And after taking the average, we can come back to Landau-Lifshitz equation. So Hamiltonian and dynamics is exactly the large U limit, Landau-Lifshitz equation. So this is a formal extension. Yeah. So here M is the classical degrees of freedom, but the effective model is going to be classical Heisenberg. Equation motion this one. Mm-hmm. Yeah, this is a perturbation from large U limit. Yes. Okay, so this is just a formalism in large U limit. I just showed our approach reduced to the large U, this equation of motion. We don't change any equation. Yeah, we show this analytically. Yeah. So if you say large U, our dynamics is reduced to this Landau-Lifshitz automatically. Well, yeah, we just need to think of perturbation. So in this case, we just need to think of the hopping in the component is parallel to this one, and the hopping term acquires some phase, and we can think of the simple perturbation. Then actually we have this m dot m. Yeah, I mean hopping amplitude depends on m. So thank you. So we check the SQ omega. It's kind of intermediate U. So this is comparison to exact diagonalization, and our Yes. Yeah. Mm-hmm. Yeah, we deduce the 40 square over U. So our approach captured a kind of spin wave. This is the small system size, but still it's reasonable results. The difference is only like 10% the energy shift. So this is the SQ omega or magnon dispersion as function of U for square lattice in this system size. It's kind of large, and we found that energy scale is going to large. U decreases, again becomes small. It's similar to net order. And the dispersion relation is quite different from the larger limit. So larger limits, the dispersion is simply the linear spin wave. And in intermediate U, we have interest in the dispersion. And in small U, we also find the interesting feature that the magnon decays into electron hole continuum. So for example, around here, the amplitude is very, very small because magnon decays into a continuum in small U. We also did some analytical calculation. It's simply the Hartree-Fock RPA. So we used mean field approximation for the Hamiltonian. And we can realize the bilinear form. And we assume the net order for square lattice and simply calculate a response function. And we use the RPA approximation. And this is the result. So we found that we can identify the electron hole continuum and magnon dispersion. And we compare this result to our simulation. And results are completely consistent with each other. So what we are doing is actually the RPA at 0 temperature. The advantage is that we don't need to assume any order. In the analytical calculation, we need to find a good ground state. But in our simulation, the ground state is chosen automatically. So that's the advantage. And also, we can extend our approach to finite temperatures. So our approach is extension of the RPA from 0 temperature and also extension of the lambda heuristic from large U case. And this dispersion is somewhat comparable to strontium irradiate. For example, if you look at the ratio between magnon energy scale and charge gap, which is kind of 2, 1 and 2, and it's similar to this spectrum. So we suspect this material has U is roughly 40 something. You also calculate some frustrated case. We introduced certain years hopping. So advantage is that we can calculate many hopping, even phase or lattice. There is no restriction. So we try to introduce some third nearest hopping. It's interesting to see the evolution of magnon dispersion. And finally, going to some different liquid states. We need to carefully consider this phase, but it's different from there because of the frustration. And somewhat, this dispersion is comparable to experiments. That's what we are doing now. Also, we can calculate the SQ omega as a function of temperature. So this is a cubic lattice, so there is a finite temperature phase transition. And we found that some interesting features, for example, magnon dispersion, magnon peak broaden, temperature increase, and also magnon peak shifts somewhat like 10 to 15%. And also we found incoherent peak around 0. So these features are also observed in experiments. And finally, I showed another interesting example of our approach that we calculated SQ omega for non-coplanar ordered state for conglomerates. We chose several these parameters for kind of large system size. And this is the ground state has the octahedral non-coplanar ordered state. So so this is the schematic picture of ground state. And we found that the several branches of the magnon. And we can calculate easily this one. Okay, so let me summarize my talk. So we have developed the kind of a new numerical method can capture the dynamics of a model in intermediate U and finite temperature without restriction of lattice, dimension, and electron fitting. And this approach is relevant to 4D and 5D electron systems. And as I mentioned, our approach is reduced to classical spin analysis in a larger limit and RPA analysis at 0 temperature. And yeah, let me mention again, the advantages are the spatial fluctuations are correctly captured. So the universality class will be correct in terms of the magnetic order. And we can calculate large system size, larger than 10 to the 4th. And there's no negative sign problem. We can apply this approach to many kinds of systems. Many types of hopping, even phases, and dimension lattice electron fitting. So I think this is a very powerful method. And the future plan is to compare the results with the experimental data of 80 days in detail, and also other cases. And we are trying to formulate also another response like optical response. If you have nice materials which has a 4D and a 5D electron system, please let me know. We can calculate static and dynamical properties quickly with very large system size and many wide range of parameters. Thank you very much for your attention.
I think I probably missed something, but is there also a way to somehow perturbatively treat Magnon interactions here in this method?
So this method is reduced to linear spin wave. So higher order, quantum fluctuation is not included in this approach. Is it clear?
Any other? Yeah, please.
Then following the question. So then, for example, simple thing like the square lattice Hidemaro model at pi 0, you have this damping at.
Oh yeah, that's because of quantum fluctuation.
So this you cannot. To what extent you can capture that in your calculation?
Is that again?
To what extent you can capture this like either Magnon scattering or the deconfinement, from your method?
What is extent? So our approach includes 2 Magnon excitations. So we have some, small continuum, but which is not quantum fluctuation. So yeah, but it's not easy to tell, 2 Magnon and quantum fluctuation.
Then another related question is, you have studied this triangle lattice Harvard model, and you get a phase diagram. So you have 4 different phases, right?
Oh, as a function of U?
As a function of U. So then, what are the type of transitions between these 4 different phases? It's all second order, or?
So this is a square, so there's no phase transition. So what I show.
I mean, for the triangle lattice.
Oh yeah, triangle lattice.
At 0 temperature, as a function of U. Yes.
Yeah. Yeah, in our approach, phase transition is basically first order. So suddenly order changed here. Yeah, function of U. Yeah. It's not easy to study the quantum phase transitions in this format, but we can capture finite temperature phase transitions.
Okay, any other questions, comments? Well, if not, let's thank the speaker once again.